Welcome back to the next video, everybody. Today we're going to review the main theorem of chapter 9 on universal deformation rings, their existence and their main properties. And we're going to look at some reductions in the proof of the theorem. Okay, so let's recall some definitions from last video. O is a noetherian local ring with residue field K. C is the category of local topological O algebras A, satisfying two conditions. The map from O to A mod MA, where MA is the unique maximal ideal of A, is surjective, so that K is also the residue field of A. And the map from A to the projective limit of its discrete Artinian quotients is a topological isomorphism. Okay. Also, we'll let V be a K representation of some profinite group G. A deformation of V to A is an isomorphism class of A representations W of G, for which W tensor over A to K is isomorphic over KG to V. And we'll write DVA for the set of such deformations. A morphism F from A to A prime and C induces a map F lower star from DVA to DVA prime, sending the class of a representation W over A to the class of W tensor A prime over A. Okay, so this was all in the last video. We'll also recall the main theorem of the chapter from last video. So theorem 1, the universal deformation ring. If V is absolutely irreducible, then there is a ring R and C and a deformation D and DVR, such that for all rings A and C, there's a bijection from C maps from R to A with DVA, given by F maps to F lower star of D. 2, the pair RD is determined up to unique C isomorphism by the first property. 3, R is noetherian if and only if the K dimension of H1 of G and KV is finite. 4, if R is noetherian, then R is M-adically complete, where M is the unique maximal ideal of R. And for each A and C, there's a well-defined bijection from O algebra maps from R to A with DVA, given by F maps to F lower star of D. So first of all, let A and C be noetherian, then the topology on A equals the MA-adic topology, and A is M-adically complete. Furthermore, every O algebra homomorphism A to A prime with A prime of C is continuous. So we saw last time how if we can prove this proposition, then we'll be able to prove 4 pretty easily. Okay. Also, by proposition 1, the category C prime, whose objects are complete noetherian local O algebras with residue field K, and whose morphisms are O algebra homomorphisms, is a full subcategory of C. Okay. So now let's look at C. We're going to record a fact here that we'll use in a later video in the proof. So we'll use the fact that a closed sub O algebra A prime of a ring A and C is also in C, which actually just follows from the standard commutative algebra fact that a sub-O algebra of an Artinian ring in C is an Artinian ring in C. However, we should caution ourselves, if A is in C prime, it actually doesn't have to be the case that A prime is in C prime. Okay, so that full subcategory doesn't have the same property that the full category does. Let's also recall some standard representation theory facts. Let V be a K representation of G. If we choose a K basis, V1 through Vn for V, the G action on V is given by a continuous homomorphism rho bar from GLN of K. We'll let W be a representation of G over some A and C, such that W mod MAW, which is W tensor K over A, is isomorphic to V over KG. By Nakayama's lemma, there exist elements W1 through Wn in W, such that Wi maps to Vi, which form an A basis of W. So we kind of lift the basis. The G action on W is then given by a continuous group homomorphism rho from G to GLN of A, such that the composition G to GLN of A to GLN of K is nothing but rho bar. So we've seen all this before as far back as like chapter 1 or 2. We'll denote the set of such rho by hom rho bar G to GLN of A. Okay, so these are like the representations from G to GLN of A that kind of reduce to rho bar. Okay, so proposition 2, there is a ring RB in C and a map rho B in hom rho bar from G to GLN of RB, such that for each A and C, there is a bijection from C maps from RB to A to rho bar maps from G to GLN of A. And this map sends a C morphism F to the composition given by G maps to GLN of RB under rho B, and that maps to GLN of A under F. And of course, the pair RB rho B is determined up to unique isomorphism by this property by the usual category theory nonsense. Okay. So what is RB? RB will end up being the projective limit over the discrete quotients of G of complete O algebras that we described above. Okay, and by above, I mean in the last video. The map rho B gives a representation WB equals R to the n sub B of G over RB, such that WB tensor K over RB is isomorphic over KG to V. What we'll end up doing then to conclude theorem 1 is we'll let R be the smallest closed sub-O algebra of RB that contains all traces of all matrices rho B of G for G and G. And then by the fact above, that recorded remark above, R will be in C. So the following claims then that we can define WB over R, the next proposition. We'll let D be the RG isomorphism class of this representation. Okay, so proposition 3, so here's the missing link there. We'll let W be a representation of G over some ring A and C, and we'll let A prime and A be an inclusion of rings in C so that A prime has the induced topology from A. Suppose that A prime contains all the traces of all endomorphisms of W that are given by multiplication with an element of G. Okay, so this is the same subalgebra we just considered. And we'll suppose that W tensor A mod MA over A is absolutely irreducible. Then yes, there is an A prime representation W prime of G, such that W prime tensor A over A prime is isomorphic over AG to W, as expected. Okay. Assuming propositions 2 and 3, which we haven't proved yet, we can quickly prove that RD is the pair from theorem 1, property 1. So we can sort of get the universal deformation ring at least kind of under our belt with some existence here. So proof, this is pretty easy. So we'll let W be a representation of G over a ring A and C, for which W tensor K over A is KG isomorphic to V. We'll choose a basis of W. And so then one can, as usual, give the G action on W by a continuous homomorphism rho in hom rho bar from G to GLN of A. By proposition 2, there's a C morphism FB from RB to A, such that the composition G to GLN of RB given by rho B, followed up by F of B, which is the map from GLN of RB to GLN of A equals rho. By proposition 3, the restriction F from R to A of FB has the property that F star D is the AG isomorphism class of W. Okay. Now, the trace of an element of G in some representation of G depends only on the representation up to isomorphism. Okay. Given F lower star of D, the map F is then uniquely determined by its values on the traces rho BG for G, big G, by definition of RB, essentially. Okay. But the O algebra generated by these traces is clearly dense in R, and F is continuous, so F has to be uniquely determined. So this finishes the proof that the property 1 of theorem 1 that we're after can actually be deduced from propositions 2 and 3. So what do we still have to do? We still have to prove propositions 1, 2, and 3. And then I believe we have to prove part, what is it? Maybe part 3 of theorem 1. Because we sort of just showed how propositions 2 and 3 give us 1, 2 follows from usual category theory nonsense. We've shown how 4 follows from proposition 1, so we're missing 3, propositions 1, 2, and 3. Okay, so we'll take care of all the proofs of those things over the next few videos. So I'll see you then, and thank you for watching.